let's do this. So we are now in week 11, which talks about trees. Okay, so trees are a type of list, if you want to call it that, similar to a list. So the terminology is slightly different, and the arrangement of these links, if you want to call them that, is slightly different. So first of all, just a quick overview what a tree is, or a binary tree. That's what we're going to talk about today, mainly. A binary tree has a root, right? So if you imagine the links that we used to have before, instead of links, now they're called nodes, right? So each of these, the A, B, C, D, E, F, G, all of these are called nodes, okay? The topmost node is called a root. Every root in a binary tree has at most 2 children, right? So there's only 2 children connected per parent. There's parents, there's children, and there's leaves, okay? Leaves are nodes that do not have any children themselves, right? So which ones are the leaves here? H, right? D is the left child, right? So H, I, J, those are your leaves, okay? NG, yeah, NG, N-E, right? So H, E, I, J, G, these are all leaves, okay? There's a left parent, there's a left child, right child, each of those has a parent. There should be only one path from the root to any particular node. So there should be only, for example, if I wanted to go from A to I, the path that I need to take is from A to C to F and then I, okay? If there's more than one paths that connect the root to the child, it is not a real binary tree, okay? There's maps which do these kind of relationships where you can have multiple connections between the different nodes, but we're not doing maps yet, or graphs, I mean. Another thing, there's a relationship in the binary tree where every left child is less than the parent and every right child is bigger than the parent, right? So B is less than A, C is greater than A, F is less than C, G is greater than C, right? I is less than F, J is greater than F, and so on and so on and so on. So that is the relationship of parents and children, and the different terminology. And of course there's different levels, right? This is G level 0 where the root is, the one down is level 1, level 2, etc., etc., etc. So let's have a look at what I have here for the trees lecture. And again, that's from these 2 books. That's some of the terminology. I'll let you read that on your own, right? I'll talk to you about the path, right? So the path between any, let's say, root to any child should be only one particular unique path. And there's an example in here which is non-tree, right? So that's not a real tree. What's a parent? What's a child? What's a leaf? Subtrees, right? You can see in here that there's a subtree right here. There's several subtrees in here. And visiting means as you go through the different paths, right? You basically visit each of these nodes. Visiting means that you could do something with the nodes, like you can look at it at the very least, right? If you wanted to just go to a node and show what the data that's stored in it is, then that's an example of a visiting a node. And keys are the actual values that we have stored in these different nodes, which is similar to how we had it with the links in the linked list, right? So every link had its own data. Those are the keys, basically. And I already explained to you that if you have a binary search tree, the left child is always less than the parent, the right child is always greater than the parent. And because of that relationship, what you can find out, you can easily find out the smallest element by just going left, left, left all the way down to from the root, right? So if I start at the root and I go left and I go another left and I go another left, and basically that's the dead end, that will be my smallest. If I start at my root and I make a right and then another right and I get to the farthest right I can, which is this, and I can't go any further to the right, then that will be the max. So it's an efficient way to find the min and the max. Yeah, that's the relationship, and you can see how things get inserted here. You can play around with, I have a tool, I have to add it. So there's let me go to the other class. I'll add these links for you too. Okay, so if you go to this here, all right, there's a, I don't know which university this is, but there's a tool in here which allows you to basically insert nodes into a tree. So you start with a blank one, and let's say, all right, I'm going to start with a 10. I'm going to insert that thing. Then I want to insert a 5. Then it's going to show you that it inserts to the left. I want to insert 20, right? Okay, so tell me, if I wanted to insert 15, where is that going to go? Left of what? Left of the 20, all right, 15, all right. And if you want to, you can see, you can pause this thing, right? And let's say I want to insert 14, where's that going to go? Left of the 15, right? So I go 14 and I go insert, right? And then you can tell it to step through this step by step. So step forward. Right, so now it's looking, this is the algorithm, it looks to see if the node that I'm trying to insert, if it is greater than or equal to 10, which it is, right, then it's going to go to the right, look at the right subtree, right, so we're going to go step forward, then it goes to the next one, then it checks to see if, one more step forward, all right, now 14 is less than 20, so look at the left subtree, so it's going to go to the left, step forward, and again, now it's going to look at if 14 is less than 15, which it is, and it's going to try to go to the left. If there's no more left to go, then it will just insert itself in that particular place. And that's how it works. And you can play around with these to visualize how things get inserted if you like. I'll add the links for you. And that's how this works. There's unbalanced trees. So if I am always inserting nodes in a particular, in a specific order, like in other words, if I wanted to go in there and let's say I wanted to insert 1 and then I want to insert 2 and then I want to insert 3 and then I want to insert 4, right? What I'm creating is I'm creating an unbalanced tree, right? So if you insert the nodes in a predictable manner, then you're going to end up with an unbalanced tree. And what's an unbalanced tree? Well, in this particular example, you don't have any left nodes, any left children, so it's all right children, and you can end up having these unbalanced trees or unbalanced subtrees if your insertion, in order in which you're inserting these things is not necessarily random enough. Okay, but if it is random, then you should generate a relatively balanced tree most of the times. Okay. Looking at the code, what this is I told you it's very similar to a link. It's actually kind of similar to a double linked list, except you don't have previous and next. You only have left next and right next, right? But again, we're using pointers and we have a data in there and my constructor and all that good stuff and a way for me to display the nodes. So that's all there is. That's all the information that is in each of these nodes. The data doesn't have to be just a single integer. It could be a whole bunch of other things, and if it's a whole bunch of other things, sometimes it makes sense to create a pointer to another class which has all these different things bundled up in it, right? If you have like 20, 30 different data items, you don't want to list them all in the node. Put them in another class which has all the data items, call it, data items asterisk data or something, and you have a pointer to the data items. Okay. The tree class, right? It has a root, right? And of course, it has a way for you to get it started. So initially, the root is equal to null when there's nothing in there. And again, this is very similar to, again, the linked list, where you have like the linked list app, which has the pointer to the first link, and then it goes off from there. So in here, you have a tree. Okay? And in there, we should be able to, do different things. Like some of the things that we should be able to do are find a particular key, insert a particular key, go through the list, display the tree, right? Find the min, find the max, delete a link, right? Those are some of the things that we need to do. So the algorithm to find a tree, to find a specific link is, let's say we're looking for the 57, right? So we're looking at 57. We're starting at 63. Is 57 less than 63? Yes, it is. Go to the left. Is 57 bigger than 27? Yes, it is. Go to the right. Is 57 bigger than 51? Yes, it is. Go to the right. Now, is 57 less than 58? Yes, it is. Go to the left. And there's two possibilities. Either you're going to go all the way to the bottom and there's nowhere further left to go, in which case you haven't found the link, or you reach the link and then you stop and then you found it. Okay? Make sense? So it's all left, right, right? If the link...
Use a loop for that, right?
You can use a loop, you can use recursion. There's different ways to do it. But yeah, loop will a lot of times will make sense. And here's the actual thing. This is what it works. This is what it looks like, right? So you have some kind of so this is your find method, right? And it's going to return a pointer of the node type, right? So when we find the node that has the key, we're going to return it. That's what it's doing. So we started the current at the root, and we keep going while the current data is not equal to key, basically until we find the data. And if my current, if my value that I'm looking for is less than the current data, I go left. Otherwise, I go right. And then if at any point my current becomes equal to null, I exit the loop, I return null, I couldn't find it. Okay, so that's the search. It's not very hard, right? Just go left, right, yeah, I don't know why I have it twice. All right, and the efficiency of this is log 2n, right? Log base 2n, okay? Inserting a node. Okay, so inserting a node works pretty much the same way. You start at the root, and you keep going until you find the correct place to insert this. Let's have a look at the code real quick. All right, so first of all, I look first if root is null. So if root is null, it's an empty tree. So all I have to do is make the root equal to this new node that I'm trying to insert. And otherwise, what I'm going to do is I need a second reference for the parent. What's going to happen is the current is going to move one step forward and the parent is going to trail one step behind. We need this because similarly to how we were doing insertion and deletion in the linked list, remember how the link, if you have a single linked list, it doesn't point to the link behind. So you need to stop at the link behind in order for you to do these different things. That's why we have a parent in here. So the current starts at root, right? And parent is going to keep moving behind. So basically, initially they're all parent and current are equal to each other. And by the way, if this stuff is hard to visualize, I highly recommend that you draw these out in Excel spreadsheet. Which is what I have in here, right? And I'll get to this when I show you how to delete different things. This is actually Java code, but whatever. It's similar to the C++ enough so that you can get the idea. Okay, but it's very hard to kind of trace all these different steps in your head. So it really, in order for you to learn this, just like with the linked list, you got to go in there and draw it out. Even this is even more so than the linked list. Okay, it's almost like it's impossible for you to visualize how the deletion is going to work without drawing it all out. Okay, all right. So let's have a look at what's going to happen here. So all it is just keep in mind what happens is parent is one step behind the current, and the current goes left and right depending whether your data is less than the current data or greater than the current data. Okay, so that's all there is. Okay, so you can either go left or go right, and if at any point you find that current is equal to no, you return, you make the parent's left child equal to the new node. So in other words, you erase one and you reconnect the other one in there. Okay. Let's see. If I wanted to, let's see if I can do this. We have enough time. Let's see if I can do this. So here's what I would suggest. All right. So you grab this thing, you grab this whole thing, right? Get it, all right? I don't know if there's any pictures in there. No, there isn't a picture to illustrate this. And you grab that picture, and you go in there and you throw it somewhere in Excel, right? There you go, paste. Okay, and then what you're gonna do is you're gonna go and trace these steps. You know, trace this step by step as you're going through the code. Okay, so in order for me to visualize this thing, I'm gonna have to create some kind of a tree. So let's say, let's go look at my tree that I had in here. All right, and let's reload it. All right, so I have a 20 insert. Let's have a 30 insert. Let's have a 10 insert, and maybe a 5 in there, and 6 in there. Okay, I might be making it more difficult than I have to for myself, but whatever. Okay, so let's say I'm going to try to insert a 4. Okay, so I'm going to grab this tree here. I'm going to copy the whole thing, and I'm going to go in there. I'm going to paste it. All right, great screenshot. Let's try it again. What is it? Oh, there you go. It's not zoomed in. Last time the charm. There you go. Okay, so this is my tree, and then I'm going to try to visualize step by step how this thing is going to move along, right? So what did I say? I'm trying to insert. I'm going to try to insert a 4, right? So trying to insert. Let me copy one of these big fonts here. I went right in there. Let me move it to the right. Okay, so what I'm trying to do is, if I could copy it, trying to insert 4. Okay, so let's see how this thing works out. So you start drawing some shapes in there. Let me just copy a couple of them from the other sheet. All right. So first of all, I am making a new node which is equal to basically a 4, right? So if you want to, you can go in there and draw yourself some circles or whatever. There you go. Fill, I don't know, one of these. Maybe make it a little transparent. I'll throw a little text on top of it. So I'm gonna put a little text box on top, and I'm gonna put what's this? 4. Nice text color. God, why white? Black. There we go. All right, so I'm trying to insert the node 4. That's what I have created here. So this is the first thing. This is the first thing you did, right? So that's the node. I just made it. Okay. And actually, did I even make it? P new data. Yeah. So both of these lines are basically creating my new node, right? So first I'm creating a new node. Then I'm telling the data is going to be equal to 4, right? So this is assuming here that new data. Right, new data is equal to 4. Okay, so that's what happens here. So initially, I made a node which is 4, right? And the first thing that I'm going to check is root equal to no, right? Is root equal to no? No, it isn't, right? So I'm going to skip that part altogether. Then I go into the next one, right? And then I'm going to make a current equal to the root, right? So I'm going to go in there, I'm going to say, all right, this is my current, And again, I just grab my little text box and I write a current here. Current. You might want to have to adjust your font size a little. Alright, and make it 16. Alright, good enough. Okay, and maybe change the color to something. Color, maybe I'll make it orange. This kind of orange. No, not that one. That kind of orange, right? So this is my current here, and then once you make one of them, you can start moving it around. Okay, so that's my current initially, right? Current is equal to my root. Then I make a parent, and then in here I say parent is equal to current. All right, so in this step right here, I'm going to change colors now, just so that I can tell the difference. All right, let's go with blue. Let's go with all the gang colors. So current, right? And at this point I said parent is equal to the current. So I'm going to copy this thing, paste it in there, move it on the other side. Alright, and I'm going to call this my parent, and I'm going to change the font color to this to I don't know, this. Okay, so that way I know that this blue arrow caused this text right here, right? So this is what it is initially, right? At this point, this is my current from this step, and then this is my parent from the next step. Okay? And then I go to the next one. All right, so is my new data less than my current data? So is 4 less than 20? Yes, it is. So now my P current is equal to my P current left child. So then I'm going to just grab this thing here. And by the way, if this was originally my P current, then you could say that this right here is my current dot left child. Right? Based on the arrangement that I had based on this orange arrow here, if this is my current, then this is my current left child. Okay? Maybe I should zoom in a little more if it works. Or not. Come on. There you go. A little better. Can you see it?
Yeah.
Okay. All right, so then we said that this. Now we're going to go to the next one. You said that the new data, the 4, is less than my current data, which is the 20, right? So that means we're going to go to this place right here, inside this if, right, here, and I'm going to say current is equal to the current left child. So now the current is going to get moved from here to there, and that's why I like to use different colors, because now current changes to blue, right? That's the effect that this blue arrow had. Okay, so what can we see? This is my parent, one step behind, and this is my current, one step forward. Okay, and then it's going to keep going that way again, and again. So let's go to the next one. So we're going to go conveniently. I think it's going to. So now at this point, what I would do is I would just do this. I'm going to just get this, and I'm going to copy this and this. And this, and this, and this whole picture right here. I'm going to copy that whole thing, right? And maybe I can include this one here too, or not, if it doesn't want to, whatever. Okay, so let's not use that one. Okay, I'm going to copy this, and I'm going to paste it right in there. Okay, and then what I'm going to do is I'm going to change the colors of these, just like I had an orange here. I'm just gonna say, all right, hold on. This here is gonna be orange. All right, same with this one, orange. All right, so these are the old ones, and you can even move them to the side if you want a little bit, right? So this is my current, this is my parent, right? And I can even say, okay, well, just to help visualize, this is my current left child, right? This one right here is current dot left child. Okay, so that was based on the first time I went through this loop. Okay, and remember that if at any point my current becomes equal to null, then I'm going to do something and then I'm going to exit, right? So that's why the loop stops as soon as my current is equal to null, whether it's this right here in this line here, or whether it's on this line right here, right? There's a couple of returns. And if my current becomes equal to null, I'm out of that loop. That's where it stops. But it's not, we're not there yet, right? Okay, so now we're going through this loop a second time, right? And now my parent is equal to my current. So now, all right, so this blue arrow here shifts my parent from here to there, right? So now I'm going to change the color for this thing to blue, right? So now this is where my parent went. And then again, is my new data the 4 less than the current data? Yeah, so I'm going to go left, and current is going to be equal to its old left child. So in other words, I'm going to grab this current here, and I'm going to shift it now here to be equal to its own old left child. Okay, so I should change the arrows a little bit, right? This is the parent, and this is my current, just so that I can, help visualize what's being changed. Okay, so that's that. Then I'm just gonna copy this arrangement again. I'm gonna get this one, get my 2 arrows, right? Unless you want to redraw this thing every time, be my guest, right? Just copy that whole thing, go that one, all right? Okay, so this was my old arrangement, so I'm just gonna do the same thing again. All right, so this is my parent, this is my current, right? Change the colors so that I can differentiate between the old stuff and the new, right? Parent, current. Okay, so that's where it ended. And we're saying same thing again, right? So we're trying to insert the 4. Is the 4 less than the current data? Yeah, right? So now we're going to say current is equal to the current left child. So let me just grab this thing here from the top maybe, so I can recycle some of it. All right, so I like to draw like a little extra thing here. Ooh, there's the 4 in there. Okay, so this one is null. Eesh. Don't worry, we'll fix the font for you. 24. There you go. That's the null.
Which is the 4, right?
No, the 4 is different. Damn it, where did the no go? Shit. All right, one more.
You got one with the background, I think.
Did it? Where?
Try to make it transparent. Or no fill.
Let's just add another one. Insert text. No. And change the font size of this thing to like, what was it, 24 or something? There you go, that's the no. Okay. All right, so I'm going to grab this. I'm going to throw it right here, right? I'm going to draw myself a little arrow. All right. And believe me, this really helps. If it helps me, it will help you, hopefully. All right, and if you don't do this, I don't know how you can possibly visualize it. Okay, so this is my arrangement, right? So my current, let's see from before because I already forgot, right? Okay, so current is here, parent is here. Okay, I copied the whole thing. Too bad. So I'm going to erase this, right? So this was my old arrangement. I'm going to change these things again. All right, this is orange. This is orange. All right, the orange indicates that it's the old one. So this is my current, old current. This is my parent, my old parent. Okay, so and the same thing. So now we're trying to insert the 4, right? So we're going through the loop one more time. So now my parent is equal to my current. So the parent gets shifted here because of this arrow. All right, so this arrow changes it here. I'm going to move this one out of the way. So this is my parent now. All right, change this to blue. Okay, and then again, my data that I'm trying to insert is less than 5. 4 is less than 5. So now my current is equal to my current left child. So now my current is going to get moved from here to here, right? And I'm going to change the color. So now this is the current. Okay? So far so good? And at this point now you can see that the current is now equal to null. So for the first time we're going to get into this if here, right? So current is equal to null. So what are we saying? Parent left child is equal to the new node. And what's my new node? It's this bad boy right here. All right? So that's my new node. All right? So I'm going to leave it like that. So this is where it stopped. So what I'll do is I'll copy this one more time. If I can grab all of them. All right, And this one, and this one, and maybe one of these arrows, and this picture. I'm going to copy it. Whoops, damn it. I had already done it. Well, whatever, you get the picture, right? So let me erase this piece. That's why it wasn't working out. But at least, hopefully, you followed. Okay, so we got to the right place. That's the main thing. I kind of messed up my order of things, but whatever. So this is my parent. This is my current. Let me copy these again. This, and this, and that. All right, there you go. Copy that whole thing, and I'm gonna paste it down here. Hopefully, hope for the best. Okay, so now for the first time, we're actually in here, right? I'm gonna erase this. Damn it! What happened? Undo. Okay. Click off of it. Get rid of this one. Okay, so this was my arrangement. So now I'm saying parent left child. And which one is my parent left child? So let me just change the colors again to orange so we know what we were working with from before. So this is my parent. This is my current. Right? This here also happens to be the parent left child. So I'm going to copy this here. I'm going to throw it right here. Come on. Parent dot left child, right? And what I'm actually saying is we're going to make this here parent left child is equal to the new node, right? In other words, instead of this being null now, I'm going to change it to 4. And I have basically inserted the 4 in there. Okay? Got it?
That's super helpful.
That's how it works. And it really, I mean, I hope you realize that when we started this thing, good luck trying to visualize what's happening, but if you trace it step by step the way I did, it becomes trivial. Right? It's like it's right in front of your eyes. And if you ever get lost, go one step up, see where you ended it. Right? I think I messed it up at some point, so I think I skipped a step, but whatever. You got it. It's on the video. So look at the video. All right, so this is how you insert, right? And if you want to insert on the right, you do the same, same thing that I just showed you. Go through it and then insert into the right. And if you want to define, it's actually the defining piece is kind of easy to see. Okay, so this is how the insert works. And a little talk about the efficiency of binary trees. They become very efficient if you're dealing with, let's say, for example, if I'm trying to find the smallest number in a tree of 1 million things, right? So a tree with 1 million possible nodes would have 30 levels, right? If it is a balanced tree, of course. If I kept inserting them all to the left and left and left and left, you would have 1 million nodes, right? But if it's a relatively balanced tree, and that should tell you that the trees are good for something that's relatively balanced, then you could find the smallest number with no more than 30 guesses. So for 1 million numbers, if you can find the smallest in 30 guesses, that beats the binary search by a whole lot, right? If I'm trying to find a number. Okay. And then there's some relationships between the number of the number of nodes and the number of levels. It's log 2 n plus 1, where n is the number of nodes. And you can represent trees with arrays as well, right? So in fact, one representation of a tree is exactly with an array. There's an actual relationship between the parent and a child and a parent. So you can go to any child and figure out what the parent is, and you can go to any parent and figure out what the children are, all right? And that's the relationship right here, all right? So the left child is the index of the parent plus 1, so 2 times the index of the parent plus 1. The right child is 2 times the index plus 2, and the index of the parent is the index of the child minus 1 divided by 2. That's how it works out, okay? And you can play around with this to see how it works, okay? There's also different ways for you to traverse the trees. There's an in-order traversal, right? And the in-order traversal can be done in a couple of different ways. But the easiest, in fact, let me show you if I can get to it. So let's say I want to go to, the easiest thing is to do the computer science club and look at the links I have here for internships and work. Go to the bottom and look at Programmer Creek. And these are the different questions that you could expect at a coding interview, right? So there's a lot of them. They're like strings and arrays, right? Hopefully you could do a lot of these. There's matrices, which are two-dimensional arrays, linked lists, which we covered, right? And trees, right? Heap is a special kind of a tree where the biggest thing is all the way at the root, or the smallest is all the way at the root. And there are the different, this is, what am I telling you about? This was in-order traversal. Okay, let me look at the in-order traversal so that I can show you how you can do this in different ways. So, and again, this is Java, but whatever, it's the same idea. Syntax is slightly different, but pretty much the same thing. So if you wanted to do an in-order traversal iteratively with a loop, then what you would have to do is you would have to go through there and then use a stack and push on the stack as you're going through there with a loop, right? And then et cetera, et cetera, et cetera. So you can see that this is, relatively long, right? But if you wanted to do this with recursion, the code becomes a lot simpler, okay? You no longer have to use any kind of a stack. You just go left and right recursively, and then it pretty much ends, okay? So let's have a look at that real quick. If I have it in there, I don't know if I have any pictures to demonstrate this. Ooh, look at that thing. Damn, I'm surprising myself. Okay, so I have a tree in here, right? So this is my tree. You have a 60 here, a 20, a 10, 40, 30, 50, right? And then I've drawn a bunch of pictures in there, right? So the in-order traversal is basically, if you look at this thing here, right? This is the function itself that will visit all these different nodes in a specific order, right? And the order in which you're going to visit these nodes, and by visit I mean the cout right here. So it depending on where the cout is, and if you remember recursion, just by moving the cout in different places of the recursive function shows the order of things change dramatically, right? So in here what we have is we have one recursive call on top to tell it to go all the way to the left. Then I have the visit, which is show the data, and then I have another recursive call all the way to the bottom, which shows does some other magic. Okay. So, and again, the best thing to do really is to just throw it out, put the code in there, and throw it in Excel and step through it step by step, right? So what happens here? I have drawn some arrows. Is you're going to go first. You're starting at the left. You're going to go left, right? So first of all, remember how when we go to this recursive function, this thing is going to keep calling itself. So it calls itself, it goes to the left, and then it's going to go back, and it's going to call itself, and it's going to go to the left, and it's going to keep going and going and going to the left until we can't go to the left anymore, right? Until local root is not equal to the no, okay? So in other words, I start at the 60, and I go 60, 20, 10, right? And I don't know why the 70 is not first. Where's the 70 showing up in there?
Right.
Yeah, but I think it should have shown first. So it should be 10, 20, 30, 40, 50. Oh, yeah, this is what it shows. My bad. So this is I guess this is the order in which I inserted the trees, right? So this is how I inserted the tree on top right, right? The top right, 6, 20, 70, 10, 40, 30 is how I inserted the tree into the tree, and this is how it will be shown based on this in-order traversal algorithm, right? So we start at the 60, first jump is the A to 20, second jump is the B to the 10. Then when I get to the 10, we're going to try to make another jump to C. Well, C is no, right? And at that point, then we're going to go to the middle piece, which is the D, and that's when we visit the link and we show it, okay? So as soon as we visit the link, then the next recursive call is to try to go to the right. There's nowhere to go to the right. And then we come back from where we're called, which was the 20, right? And as soon as we return from the 20 call to the left, then we're going to try to do the next one. This is the G. We're going to do a C out there, right? So now we're going to show the 20. Then the next one is the H. From 20, we're going to jump to the 40, right? From the 40, we're going to try to go left and then left again, right? We're going to hit a dead end, and then we're going to show the 30. We're going to try to go to the right. Nowhere to go. We're going to come back to the 40, show the 40, then go to the right of the 40, right? Which lands us at the 50. From the 50, we go left. Nowhere to go. We return back to the 50, show the 50, which is the Q here, right? I have C outs in there, right? Then you're going to try, after you show or visit the 20, the 50, you're going to try to go to the right. Nowhere to go to the right. And then you're going to go return back to the 40, show the 40, okay? And then when you show the 40, then you're going to come back. I forgot my letters now, so it's S, yeah. So at the 40, from the 40, we return back to the 20. From the 20, we return back to the 60. As soon as we return back from the 60, we have come back from all of our recursive left calls. Now it's time to show the 60, which is the letter V, right? I almost ran out of letters. It shows the 60. Then from the 60, after we visit the 60, we go make a right, right? That shows us we landed the 70. From the 70, we try to go left, nowhere to go. Then we return back to the 70, show the 70, try to go to the right of 70, nowhere to go, and then return back to the 60, and it's done. Okay? So that is the in-order traversal. And in fact, these are some of the common questions that you can expect in a job interview is exactly those kind of things. Right? So it's not that hard for you if you put in the time to visualize it and draw it out and stuff. You can see how an in-order how an in-order algorithm works, how a pre-order, a post-order. There's different ways to traverse this. And this is the in-order traversal, right? All it is you have an in-order recursive function which keeps calling itself unless this local root becomes equal to null, at which point you basically have hit the dead end. And if you ever hit the dead end, then you return back to the recursive function call, do a C out, which is basically visiting, displaying the node, and then you try to go as far right as you can. Okay? There's also pre-order and post-order traversals. I did not go in detail to draw those out. Those are used they're used for if you try to format your equations in a specific notation. So the regular notation that we're using is the infix notation, which is you have some variable, then multiplication, parentheses, then whatever b plus c inside of the parentheses. Another way to do this is you can have a prefix notation. The prefix notation, you have kind of the order of things. So you start right to left. So the first two things on the right are b and c. You're going to add these two things. And then the result of these, let's say b plus c is equal to d, then you're going to have basically asterisk AD, which is the result of b plus c. And then the next thing you're going to do is you're going to multiply a times d, which is the same thing as doing the thing on top. Okay? And the prefix notation is a, b, c plus an asterisk. All right? So it's basically first you do the b, c addition, then you do the a times BC with the addition. Okay, so this is just a different representation of an algebraic expression, so the pre-order. So the pre-order, if you wanted to do it with the prefix notation, all you got to do is rearrange how you do the recursive calls. So you're going to do the C out first, then you're going to do the left recursive call, and then you're going to do the right recursive call. Okay, so that's that one. And if you wanted to do the postfix notation, then you do the revisitation all the way at the end. Okay, and then you do the left first and then the right second, and that's your postfix notation. Okay, to find the min and the max, I already told you. All you got to do is start at the root and go left, 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 left until you hit a null, and then you found the min. If you want to find the max, you go right, right, right until you get to the max, and then you know that's the end of it. Okay, so I can actually give you those in there. All right, so the whole code is in here. And I haven't, there's a display, the display tree which uses nodes to, it uses stacks to show these things row by row. Okay, so there's that in there as well. So when you run the program, it will show you like a little text, arrangement of all the different nodes, like a little triangle. So it will be arranged like a tree. Keep in mind that you don't want to have the tree too many levels, because it's not going to be able to show the whole thing the right way, right? So keep it to like 4 or 5 levels if you want this thing to show correctly. And I have that in there. Oh, there you go. This is what it looks like, right? So if I insert a bunch of if I inserted 61398 into the tree, then it will look like this right here on the bottom, right? So it will look like that. So what you have to do is implement and test all the following tree methods that I showed you: the find the min, find the max. I'm actually not even touching the delete business yet here. But I will show you what the deletion works like in Java code, which is very similar to C++. But let's just visualize how that works. Okay, so the only thing in Java that's different is, well, there's a couple of things that are different. Number one is it doesn't have any pointers, right? They simplified their life quite a bit by not using pointers. All right, so let's say. But it works pretty much the same way. The other thing about Java is it automatically handles deletion. So as soon as I delete a particular node, I don't have to manually go. Okay, so let's say I'm trying to delete 7. All right, so if I'm trying to delete 7, if this thing works, that'll be nice. Come on. Okay. So I'm trying to delete 7, right? So this is how it goes. We're going to start 2 variables, current and parent. Initially, they start at the root, right? And then again, I'm going to go in there. I'm going to try to find the data. Finding the data is just like finding the way I showed you already. So what we're going to do is, and it's the same thing. We're going to have a parent, and you're going to have the current. The parent is going to be one step behind the parent. Okay, so initially the parent and the current are set to the root, which is the one on the top. When I get to the loop, inside of the loop where it looks for the key 7, the parent is going to be here. Since my data 7 is less than the 10, we're going to go to the left, right? So current is equal to the left child. So now current moves here, right? So parent is here, current is there, okay? And then we're going to keep going through that loop. The next step is we're trying to find a 7, right? 7 is bigger than 5, so that means that this time it's going to go to the right child, which is this one. So, and then the parent gets shifted, by the way. Parent is equal to the old current, so which is moves it here. Current goes to the right, which is there. And at this point, now current data is equal to the key that I'm trying to find. Loop stops, and then we go to the next step. All right. So the next step is if there's no children. There's different arrangements. Or there's different cases. There's different things that we have to consider based on whether the node that we're trying to delete has any children, or it has. So first of all, let's say it has no children. Then the second case is it has 1 child, and then the third case is it has 2 children. So all these different cases have to be handled separately. And in order for you to visualize how it works, you got to draw the pictures, okay, for any of them. So all we're talking about now is we're trying to delete. I'm going to try to delete the 7 first. Then I'm going to show you how to delete the 3. And then I'm going to imagine that the link that I'm trying to, or the node that I'm trying to delete is all the way at the top, which is a root, and it doesn't have any children. So I'm going to go through all these different ones. Okay. So anyway, I'm trying to delete the 7. So my current is here, my parent is there, right? And then my current here, my current is the right child of my parent, right? Which means that when I go in this here, right? Which is if the current left child is equal to no and the current right child is equal to no, which they are, right? The current doesn't have any left or right children. Then the first thing we're going to do is we're going to look if the current is equal to the root. It isn't. Is the current the left child of the parent? No. Is the current the right child of the parent? It is. then tell the parents to have a right child of no. And basically I have deleted that thing. Okay, so that's deleting the 7. Now deleting the 3 is a similar situation. The current ends here, the parent ends here, right? And now that you're looking at current that does not have any children, right? This here, it does not have any children. Is the current equal to the root? No, it isn't. Is the current the left child of the parent? Yes, it is. So tell the parent that its left child is equal to the no, which is what you have here. Okay? So that's that. And now the last case is when your parent or current are equal to the root. All you have to do is, you're not going to go through this loop at all because the current data is already equal to the one that you're trying to delete. I'm trying to delete a 10, right? And the 10 is the root, which does not have any children. So what we're going to do is we're going to go into this thing again here, right? Does the current left child equal to no and the right child equal to no? Yeah, they are, because there's no children. Is the current equal to the root? Yes, it is. So then just make the root equal to no, and that's it. No, nothing left in the tree. Okay? So that was the easiest one, right? So this is if you're trying to delete a node which does not have any children. Okay? So now we go to the next one, which is a little bit more complicated. So now we're going to talk about trying to delete a node that has one child. Okay? So the first one is, I'm going to start with the easy one, which is, let's say I have this arrangement of nodes in here, right? So the 71 is what I'm trying to delete, and it is the root initially, just to make it easier, and it has only one child, right? So first it has a left child, then I'm going to change it so that it has a right child, right? So I'm going to handle those first two. Okay, so initially I say current is equal to the parent, which is equal to the root, right? They're all equal here in the beginning. Okay, we're not gonna go look through this. We're not gonna go search through the loop because we already found the data we're trying to delete, right? We're trying to delete 71. So then we're not gonna deal with these here anymore, right? We're not gonna deal with this section of code here because it does have one child, right? This is only if it has no children. So now we go if it has one child, okay. So if my current right child is equal to the no, which it is, right? This is my current right child. It is equal to the no. So that means we get into this if here, right? Is my current equal to the root? Yes, it is. That's the current, which is equal to the root. So then you just say root is equal to the current left child. Right? Which one is the current left child? Well, it's the 63. In other words, you're just telling it, okay, you 71, you're now equal to 63, and 71 is gone. Okay? In C++, you would have to do an extra little step where you go in there and you actually delete the link. But in Java, as soon as you say, okay, well, parent is equal to the current right child, that right child, the left child, will eventually get wiped out by Java automatically. Okay? That's the garbage collection in Java, which is a really cool thing to have, unlike C++. All right, so then we go to the next one. Delete 71 when the node to delete is the root and has a right child. So all I did is I put the 71 in here. I have a 70 right as a right child, and then I have a null as a left child. Same arrangement. Parent is equal to current is equal to root initially. We don't have to go through the loop to look for the data because the data is already found, which is it is the 71 that we're trying to delete. We're not going to go through this piece because it does have one child. We're not going to go through this piece because the current right child is not equal to no, right? But we are going to go into the next one after it, which is when the current left child is equal to no, which is what we have here, right? And is the current equal to my root? It is. So then the root is equal to the current right child. In other words, you root the 71, you're now equal to the 73. And the tree has been, the node has been deleted. Okay, and again, in C++, you would have to go and throw in like maybe one or two extra lines of code to really delete the link. But in Java, as soon as there's no other, as soon as we make, we don't have to delete anything in Java. Java handles the deletion automatically. Okay, so that is basically just handling when we have one child and that one child is the root. But there's more. So now let's say we were trying to delete the 71. Right, 71 is right here. Okay, 71 is here. And we're trying to delete a node which itself is a right child and has a left child. Right? So in other words, we're going to go through this. We're going to search it and the same business as usual. Right? So we basically, the final arrangement is current is here. Right? And this is my parent, just like before. Okay, we're trying to delete the 71. This loop goes on while the current data is not equal to the key. We found the 71, so the loop stops. Okay, so now that the loop has stopped, we're not going to look at this code, which is for no children. We're going to look at this code here, which is when the current right child is equal to null. Right, current right child is equal to null. Okay, and this is how it was arranged from before in the previous step with the loop. Okay, so if that's the case, I have to look first if the current is equal to the root. No, it isn't. We already handled those cases. Is the current equal to the left child of the parent? No, it's the right child of the parent, which means we're going to do this line of code right here, which tells the parent that its right child is going to be equal to the current left child. In other words, parent right child, you're going to be equal to the current right child, this one here. Okay? And as soon as you you're reconnecting, you're removing the connection between 52 and 71, and you're making a connection between 52 and 63. So it works out to this thing here, right? You don't have to worry about all the other nodes that are connected underneath the 63 or any of, if you have like a bunch of other subtrees in there, you don't worry about them. The connections to those different nodes are still existing. All you have to do is you have to tell the parent to connect itself to the 63, and then all the other successive connections from 63 down, they're already established, and we don't have to worry about them. Okay? So that's it. We got rid of the 71. We shifted the 63 to the place of the 71, and that's it. We deleted that one. Now let's look at the other case. Now we're deleting 71 when the node to delete is a right child. Again, we have this arrangement. You have the parent here. You have the parent right child, 71, right? But this time, instead of a null to the right of the 71, we're going to have a null to the left of the 71. In other words, current left child is equal to null. Okay? We skip this one, which is the one for no children. We skip this one because this one says if my current right child is equal to null. That's not the case. We go to the one where it says current left child is equal to null. Current left child is equal to null. So we're getting into this one. Is the current equal to null? Nope. Is the current the left child of my parent? It isn't, right? Current is the right child of my parent, which means I'm going to go into this code right here, into this piece of code, and I'm going to tell it parent right child. Parent, your right child is equal to the current right child. So in other words, this piece right here, which was the 71, is now equal to the current right child, which is this one right here. And then in effect, all we do is we shift we make a connection between 52 and 73, and that's it. And then we can go and delete the 71 in C++, or since this is Java that I'm showing you, it just wipes it out automatically eventually. Okay? So that's that. Now, since we gotta exhaust every possible option, these couple of scenarios were when my current ended up being the right child of my parent. Okay, but we can also have the arrangement where my current is the left child of my parent. Okay, so I rearranged. I created another tree. Right, I had to go in there with the visualize a tree web page, play around with it so that I have a really an actual tree. Don't just make up things and think that, oh yeah, that's a real tree, and then you try to go through it and it doesn't work out because you didn't make the binary tree the right way. Just use the tool. Anyway, current is the left child of the parent, right? So if that's the case, and my current's right child is equal to null. So now we're here, right? Current's right child is equal to the null, which is what we have here. It's not the root. but now we're here, which is basically, it is the left child. So current is the left child of the parent. So we do this line of code here, and that makes the 63, so parent left child, this is equal to this one. In other words, we replaced the 71 with 63, and then we made this new connection. And then the last possible way to do this is the current is still the parent's left child, but now the current left child is the null. So he only has a right child. Okay? So again, we go to this piece of code, which is when my current is equal to the left child. It's not the root, but it is the left child. It's not current left child. Yeah, current left child is equal to null. That's this. And then the current is equal to the left child, which is this is left here. And then what we're going to do is we're going to say parent left child, which is this here, is equal to the current right child, which is this one. And then all we do is pretty much you shift the 73 and the 74 up to where the 71 was. Okay? So those are all the different ways that you can possibly delete a node that has one child. Right? So again, it could be the node itself, which is current, could be the left child of the parent, it could be the right child of the parent. The node that you're trying to, the node that we're deleting could have a left child and a right child of no, or it could have a right child with a left child of no. Okay? So, that's that. And then the next one is deleting a node with two children. And that's the most complicated one. Alright? So if you could do these, a couple ones in your head, which are not very easy to do, then there's no way possible for you to be doing this in your head unless you're some, sort of a genius. Okay? So here's how it goes. So I have the arrangement of this right here. I don't know if you can see it. Let me zoom in some more. Alright, here we go. Okay, so I have this binary tree here, and I'm going to try to delete 12, which is here, right? You can see it. Okay, so first of all, I have to explain to you how we're going to do this. There's two different ways for you to delete. So by the way, what are we deleting? We're deleting 12, and 12 happens to have two children, right? 12 has a child on the left, it has a child on the right. There's no null attached to it. Okay, so we're trying to delete that thing. Alright, so the way we're going to do this is, there's a couple ways to do it, and scribble, curve. Alright, let's go with the scribble. So if I go from here, so what I'm going to do is, here's what I'm going to do. So I'm going to start at current, I'm going to go to the right, right? I'm going to get to the 38, then I'm going to try to go left, and then I'm going to try to go left further until I hit a no. As soon as I hit the no, right? So the algorithm the algorithm to delete 12 is we're going to have to find the next biggest node to insert in its place. Okay? How are we going to find the next biggest node? Well, there's two ways to do it. One way is you go to the right subtree, and by the right subtree I mean, where's my right subtree? Let's do a little thing here, right? So this is my right subtree here, right? So we're gonna start from the current. We're gonna go to the right subtree, and then we're going to find the smallest node in my right subtree. What is the smallest node in the right subtree? 20, right? So how are we going to find that? We start at the root of the subtree, which is this one, and we keep going left, 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 left until we hit a null. Okay? Then that 20 is going to be my successor, or what we're going to be replacing the current with. But there's a bunch of links in here which we're going to have to reconnect and do things with, right? And that's the actual harder part. Okay, so you understand how it works, right? We're going to go to the right subtree, and then we're going to find the smallest nodes, and we do that by going left, left, left. Okay? There's another way to do this, actually. The other way to do this is we go to the left subtree. Damn it. we go to the, come on. We go to the left subtree, which is, I guess, this little piece here. All right, the left subtree is the 11, right? And then we go and we find the biggest node in the left subtree. So if we're going to be replacing, we can either replace 12 with the biggest node of the left subtree, or we can replace 11 with the smallest node of the right subtree. And I'm not going to go and show you how to do it both ways, because it's way too much drawing, and I know you're falling asleep. All right, so again, we're started the current, we go right, and we go left, left, left until there's no more left. All right, so that's what it works. So we are trying to, first of all, here in this part of the code here, we're trying to find the link to delete, right? The link to delete is 12. So this thing keeps moving until the current becomes equal to the link that I'm trying to delete, and then parent is one step behind as usual. Okay, so that's that. We're not going to look at this piece here because it does not have 0 children, it does not have 1 child, it does not have 1 child, which leaves us to the last case, which is when it has a we're going to have to find the successor, right? It has 2 children, right? So the first thing we're going to do is we're going to make a separate method to find my successor, right? And that method will do the go right, go left, left, left until you hit a no, and it will establish any connections that need to be rearranged, and we'll look at that step by step, right? So node successor is equal to get successor current, right? So get successor current, right? Basically what we're saying here is we're sending current over as my argument. Del node is equal to that. So in other words, del node is equal to this one right here. Okay? So now we're going to start with that. So then I go into my del node method, right? And I'm going to do a couple of things. So I'm going to say successor parent is equal to del node, successor is equal to del node, right? So that means these 2 orange arrows right here. So that is, I'm saying that the successor parent and the successor, both of them are equal to the del node, right? That's what these 2 orange arrows are doing here. Okay? Then I say, all right, current is equal to the del node right child. That's the first right we're going to make, right? So now I tell it, okay, well, current, you are equal to this one right here, which was the del node right child. So I have moved current here. Okay? Now I'm going to go into the loop. Okay? I go into the loop and I keep going. Remember, the loop goes on until my current ends up being no. The first thing I do is I say successor parent is equal to successor. Okay, so that means the successor parent is here, which is equal to the successor. Okay, the next step is I'm going to say successor is equal to the current. So successor here is equal to the current that I had moved from before. Okay, so successor is here, successor's parent is here. And then the next thing is, remember how I'm going to keep moving left, left, left? I tell it current is equal to the current left, so now current is moved here. Okay, so the ones in black are the ones that I have just changed inside my loop. I'm going to go and do this one more time now, because the current is still not equal to the null, right? The first thing I'm going to do is I'm going to say, and the ones in blue are the old ones, right? The ones in black are the new ones. I'm saying successor parent is equal to successor. So this new successor parent is equal to the old successor, right? Then successor is equal to the current. That means the successor, the new one, is equal to my old to my old current. And then the next line right here, current is equal to current left child, moves the current right on top of this null, if you want to call it that, right? So my current is null, my successor is the 20, my successor parent is the 38. And now the loop stops. Right? The loop stops because we don't have any more current. Current is now equal to null, right? Okay, so, and here's the tricky part. So this was actually not so bad. The confusing part is right here. So what we're going to do is, first of all, this is the picture from how I have this arranged, right? This is my current, so now orange is the old ones, right? This is my current, this is my del node, that's the one that I'm trying to delete, right? This is my del node right child, which also happens to be equal to the successor parent. This is my successor parent left child, which is equal to the actual successor. And this is your successor right child, which is the right child of the successor. Okay, so that's what we have to begin with. That's where we have ended this picture, right? Okay, here's what happens. So first what we're going to do is we're going to check to see if the successor is not equal to the del node right child. Okay, so first of all, if my successor happens to be this one right here, then what do I have to do? I'm just going to grab this whole thing here and I'm going to shift it up where the 12 is, and I don't have to worry about anything else. Well, there's one little step that I have to worry about, but I can literally grab the subtree that says 387290 and then shift it up to the 12 and then just make one new connection, tell it just connect to the 11 on the left and you're done. Okay, but that's not the case. We're looking at a more complicated case where my successor is here, right, and my successor is not equal to my del node right child. So that's this here. That's what we're getting into this one. Okay, so the first thing that I'm going to do is, and this is the complicated part. So successor parent left child is equal to my successor right child. Okay, so in other words, let me zoom out a little bit so you can see both of them. What I am doing is I'm telling it, let me zoom out some more. Hope you can see it. So see how the 38 here, the successor parent, was connected to 20? Well, when I say successor parent left child is equal to the successor right child, so I'm telling it, you successor, your left child, or the thing that's connected here, is now going to be equal to the successor right child. In other words, I grab the 24 and the 27, and I connect the 38 to the 24. And I shift both of those up here. Okay, so the confusing part is that the successor is still there. The successor is still there, and it's basically, this picture right here. Right? So I still have that successor arrangement from before. The successor is the 20. The 20 itself is connected to the 24, which is connected to 27, and there's a no in there too. So that's still there. Okay? Now what happens in the next step is I'm telling it successor right child is equal to the del node right child. Okay? So what happens is it starts here, right? So successor right child, which is, I'm telling it, successor, your right child, which is what used to be the 24, is now equal to the successor, to the del node right child. Right? In other words, I'm grabbing the 38, 72, and 90, and I'm connecting the successor to those. Okay? And by the way, the 38 is already connected to the 24 and the 27, so now I have this arrangement in here. Okay? This is what it looks like. Okay? So in the first step I told 38, connect yourself to the 24. The next step is I told it, okay, successor, connect your right child to be the 38. So now we have arranged this subtree now. Now that we have this arrangement, we're done with finding the successor. So we found the successor, we arranged the links in a way that it should be arranged, and now we return back. So now we're returning back to this here. So now note we have found the successor, we made the arrangements for the successor, and then we go in there and we look at, okay, well, is it root? Is the current equal to the root? And remember, current is the del node. It's the one that we're trying to delete. Okay? So is the current equal to the root? No, it isn't. Now, is the current the left child of the parent? And I have a picture in here, right? So this is before, right? We had a parent. This is my current. That's the one we're trying to delete. This is my current left child, which is the 11, and my successor, which is 30. This was before I did any of the arrangements, right? So the first line that we're going to do is, so since my current is the right child of the parent, we're going to go into the else, right? And we're going to say parent right child is equal to the successor. So parent right child, in other words, parent, your right child, which used to be the 12, is now equal to the 20. But the 20 that I rearranged from up here. So in other words, I basically established this connection that you see in blue here, right? So I say, all right, we're going to connect 10 to the 20, and the 20 is already connected to the 38 and the 24 and the 27 and all that good stuff, and it actually has like a null in there somewhere. Okay? Okay. So the next step is I have to replace the null that this thing already had from here, right? So that the 11 goes in that place. Okay? So that's the next step right here. So successor left child, which is this right here. This is the successor left child, right? This piece right here, the null. That is my successor left child. I'm telling it, you successor, your left child is no longer null, but it is the current left child. Which one is the current left child? This one right here. So now I have actually established this connection in red that you see here. So the 20 is connected to the 11, the 10 is connected to the 20 from before, that blue line, and then I have some pictures in there to show you that too, basically. That's what happened. So this line in red, we just established this connection here where it used to be null, now it's the current left child, and voila, the thing's deleted. Okay? If you really want to learn this, do it. This time, try to redraw this whole picture for yourself, but instead of the current being the right child, make it the left child. Right? So that's basically all I want to tell you as far as trees are concerned. Any questions? If that didn't blow your mind, I don't know what will. Okay? So, and by the way, similar kind of things you also have to do for, I don't have it. Yeah, reasoned. Yeah, it's hard to find. I gotta look for it. I hope it's saved somewhere. Okay, so, yeah. Any questions? Bye. Okay? So that's it in a nutshell for today. Come see me in the office if you are so inclined.